Chapter 3. Hamilton's Principle of Least Action. We now obtain the Euler-Lagrange equations a different way, as the result of a variational minimum given by Hamilton's principle of least action. This approach is more than a Newtonian reformulation, as it is the root formulation for the complete quantum theory to be described in, and briefly discussed in Sector 3.2. Thus, this section is of special note in its part of the conceptual foundation for the fully generalized quantum, propagator theory, and emanator theory.
3.1 Lagrangian for point particle. Consider a point-like object and let's define its position by the generalized coordinates the set q sub k, where for k dimensions we have coordinates q sub 1 q sub k q sub k. Let's now introduce a time parameterization, coordinate, t, and define the associated generalized coordinate, position, changes with time, e.g. the velocities. Thus, for coordinates the set q sub k and velocities the set v sub k we have.
Equation 3-1. For time t. In early physics it was argued that variational constructs that are minimized, such as paths, or maximized, such as entropy, should determine how systems evolve, propagate, or equilibrate. In those discussions we see how the early dynamical description of Newton, F equals ma, is a second derivative formulation.
The name of the variational function of coordinates and velocities, as before, is the Lagrangian, and denoted by L. See the next equation. Where L equals L of the set q sub k, the set dot q sub k is the form of a preamble that will be often used to indicate the independent variables, variationally relevant, in the function definition, here the coordinates, and their velocities. Consider Newton's second law with no force present. The Lagrangian for this is.
See the equation shown. Or, for one dimension, have L equals 1 divided by 2 times mv squared, the classic expression for kinetic energy. To recover Newton's second law, we then set the time derivative of each of the Lagrangian velocity derivatives to 0, not the time derivative of the Lagrangian function itself.
See the next equation. Thereby recovering the equation of motion when no force is present, ma equals F equals 0. Thus, a direct expression of a variation of a function, such that setting that variation to 0 yields the equations of motion, is what is obtained in the action formulation, first expressed by Hamilton in 1834 with the principle of least action. The action S is introduced as a function of a function, a functional, defined by the following integral relation along paths parameterized by time parameter t, see figure 2.1.
Equation 3-2. Where the component subscripts are dropped, or one-dimensional case. We will assume this is a valid starting point for deriving equations of motion, and we prove this to be the case later in the analysis, where this notion of action is rederived in the Hamilton-Jacobi formulation in Chapter 8.
Figure 3.1. The action consists of the integration of the Lagrangian along a specified path. Stationarity in the variation of the action, with fixed endpoints, gives rise to the usual Euler-Lagrange equations. Two paths of integration for the Lagrangian are shown in the figure, with endpoints shared, fixed, such that q sub 1 equals q of t sub 1, and q sub 2 equals q of t sub 2. In the Hamilton formulation, the motion is given by the time parameterized path q of t that gives a stationary value for the action. Functional variation is 0. And where the typical boundary conditions is that the endpoints on paths of motion are fixed at beginning t sub 1 and end t sub 2, I dot e delta q of t sub 1 equals delta q of t sub 1 equals 0. Assuming that there is not direct time dependence in the Lagrangian, we then have for the functional derivative.
See the equation shown. The boundary term from the integration by parts is 0 since the boundaries are fixed for the variations being considered. This is the standard case for most of the variational problems that will be described. There are alternate, more complex, formulations with non-fixed ends that will be discussed as needed. Thus, we now have that Hamilton's principle of least action, standard form, recovers the Euler-Lagrange equations mentioned previously.
Equation 3-3. The Euler-Lagrange equations will be used in the sections that follow to obtain the equations of motion in a huge variety of applications. Before moving to these examples, however, there is more that can be gleaned from the action formulation than a mere recovery of the equations of motion, a variety of properties of motion and conservation laws can now be extracted.
3.1.1 Mechanical properties indicated by action formulation. Prior sections made reference to Goldstein's textbook numerous times, and some of the development, strong law of action-reaction, was from solving problems from there. Going forward, we solve in detail many of the problems presented in Landau and Lifshitz's textbook on mechanics, and follow their mathematical development in part as it is an exposition of the possible second-order differential equations that can occur. The ODE-centric approach is also done in Percival's text, so this is a popular approach. The role of ordinary differential equations, ODEs, in the development of mechanics is made even more explicit in the effort presented here, however, with a large appendix on ODEs and problems/solutions for such, drawn from notes taken while at Caltech in AMA 101, a graduate-level mathematics course on ODEs. Part of the development presented here pairs classes of ODEs with classes of motion, and from there shows how to arrive at general systems, including those with chaos. The chaos part of the discussion is mainly done in the Hamiltonian formulation similar to the textbook by Percival. Advanced dynamics sections draw from problem solutions for problems given in the textbooks by Goldstein, Landau and Lifshitz and Fetter and Waleka, and from notes from dynamics, PH 106, and advanced dynamics, AF 107, courses taken at Caltech, CA 1986.
Following the description given by Landau and Lifshitz in mechanics, let's first consider a system comprised of two parts with negligible interaction. We write the total system Lagrangian as the simple addition of their two parts.
L equals L sub 1 plus L sub 2. The additive property implies a decoupling of non-interacting systems, but with common shared constant, e.g., choice of units. To show this, consider multiplying the Lagrangian by a constant, the resulting equations of motion are unaltered, and the separate terms all share that same multiplier. Continuing along this vein, consider adding a total time derivative of a function, dependent on coordinates and time, to the given definition of a Lagrangian.
See the next equation. The new action functional obtained is, for which the variation is the same when the endpoints are fixed.
Delta S equals delta S. Thus, a Lagrangian defines the same equation of motion for any variation if differing by a total time derivative. If there are non-fixed or non-trivial boundary conditions, then there is no longer invariance upon addition of a total time derivative.
If the Lagrangian is not dependent on spatial coordinate, we say there is homogeneity in space, same for time. If the Lagrangian is not dependent on direction in space, we say there is spatial isotropy, while for time, a one-dimensional parameter, this is equivalent to saying time reversal invariance. So if we say there is nothing special about the position or time in describing the free motion of a particle, then we are saying that the Lagrangian for its motion should have no qt dependence. Furthermore, the velocity dependence must only depend on the magnitude, for isotropy, which can be conveniently written as a dependence on the magnitude of the velocity squared.
L equals L of v squared. If this is a valid functional form for the Lagrangian, then we expect no change under velocity shift, true for non-relativistic, i.e. Galilean, absolute time reference. Let's try v vector prime equals v vector plus epsilon vector.
See the equation shown, where the derivation to first order in epsilon vector is explicitly shown. For this to remain unaltered at first order, then the first order term must be a total time derivative. Since it already has a time derivative in the velocity, this is only possible if the fraction with numerator partial differential L and denominator partial differential v squared is independent of velocity, but non-zero, thus have L proportional to v squared, and by convention with Newton's specification of mass and inertia we have.
Equation 3-4. For the free particle, from which application of the Euler-Lagrange equation yields for equation of motion v equals constant, recovering the law of inertia. Note also that v squared equals dl over dt squared equals the fraction with numerator dl squared and denominator dt squared, where expressions for the metric dl squared in various coordinate systems are
Cartesian, dl squared equals dx squared plus dy squared plus dz squared right double arrow L equals 1/2 m times dot x squared plus dot y squared plus dot z squared, cylindrical, dl squared equals dr squared plus r times d phi squared plus dz squared right double arrow L equals 1/2 m times dot r squared plus r squared dot I squared plus dot z squared. Spherical, dl squared equals dr squared plus r times d theta squared plus r the sine of theta d phi. Squared right double arrow L equals 1/2 m times dot r squared plus r squared thet dot a squared plus r squared the sine squared of theta dot I squared. Equation 3-5 ABC. 3.1.2 The action for free motion.
Example 3.1. The action for free motion, minimal practical use, maximal theoretical implication. For a free particle with one-dimensional motion we have L equals T equals 1/2 dot x squared, for which the action is, see the next equation, where V equals the fraction with numerator x sub b minus x sub a, and denominator t sub b minus t sub a from EL equation. Thus,
see the equation shown. If normal triangle T equals n time steps, then the absolute value of normal triangle x almost equals the square root of normal triangle T, as with a random walk, further details in.
Exercise 3.1. Repeat with L equals hyperbolic cosine of V. Note that the action for free motion is like the solution to the diffusion equation, solution to 1D heat equation, which is our first hint of the possibility of the Schrödinger equation, and the first hint of Ito integral, Wiener integral formulations, seen again later with the Euclideanized quantum form by way of analytic time via Wick rotation c. The relation to the diffusion relation in one dimension is also an early hint of the deep connections between dynamics and thermodynamics overall, via quantum mechanics with complex time or analyticity to be discussed in the reification of analytic trigenta-duonian emanation associations or projections, with the emergence of thermality, martingale thermodynamics, geometry, standard cosmology, and gauge geometry, the standard model, is discussed further in
Example 3.2. Lagrangian with higher order time derivatives. Consider a system with the following Lagrangian. See the next equation. The equation of motion for such a system can be obtained uniquely if we require that the action be an extremum for all paths with the same values of x, and all of its time derivatives, at the endpoints of the paths. See the equation shown. And another integration by parts, with boundary terms dropped, thus total derivatives dropped.
See the equation shown. The equation of motion is thus, where the 4 denotes a fourth-order time derivative. Exercise 3.2. Repeat with L equals ax cubed plus 1/2 m dot x squared plus bx.
3.2 Least action from highly oscillatory integrals and stationary phase. The variational extremum indicated in Hamilton's principle of least action can also be obtained via an exponentiated large magnitude functional integral, where the action is evaluated along every path, each contributing an exponentiated term with a large constant factor, such that a variational minimum dominates, according to negative sign convention below. This is also used in the quantum path integral formulation, and where there is still a large constant, the inverse of Planck's constant, but the exponentiated term is made imaginary, i.e., each path now contributes its action as a phase term, where stationary phase then selects for the variational extremum. Thus, the classical integral form can be analytically continued into a quantum integral form that is directly relevant.
Equation 3-6. Note that the classical integral form was an odd representation, not much used since it reduced back to Hamilton's least action anyway. In its complex form, however, when reduced to differential form consistent with least action we get Schrödinger's equation, and recover the classical theory at lowest order with quantum corrections at higher order, see for details.
The notion of multiple paths, from which the path imparting stationarity is selected, is foundational with the quantum PI approach to quantum mechanics. PI quantization is equivalent in various domains to the operator/wave function, Schrödinger, or self-adjoint operator/Hilbert space, Heisenberg, formulations, as will be shown in, where the choice of formulation to solve a problem can be critical to its solution. The variationally defined classical constructs, especially those outlined in Chapter 8, will eventually generalize to the full quantum mechanical formulation, in terms of multiple propagation paths and a stationary action functional over those paths. In practice, the full quantum theory, especially for bound systems, is much easier to analyze if we shift from the path integral representation to one of the equivalent formulations by Heisenberg, Schrödinger, or Dirac, as will be shown in. The Heisenberg operator calculus formulation is based on an operator reformulation of the classical Hamiltonian, Chapter 6. Schrödinger's equation is based on an operator wave functional reformulation of the Hamilton-Jacobi equations, Chapter 8. And Dirac's axiomatic reformulation shifts to general systems without necessarily having a classical analog, and also bridges to the relativistic wave equation for spin 1/2 fermions in further developments.
Notice that the classical integral representation involved a simple sum on paths, no weighting, and later, with analytic continuation to a quantum formulation, we still had a sum on paths that was unweighted. This characteristic is carried over to statistical mechanics to become the equipartition theorem, and can be found via analytic continuation, Wick rotation, from the quantum propagator to the statistical mechanical partition function, described in books 7 and 8 of the series. Thus, there is a growing body of evidence that the underlying theories or theoretical representations are analytic and possibly in multiple ways, indicating possibly being fundamentally hypercomplex, discussed further in Book 9.